Picture steel rising from gravel while a new set of towers hums in the distance. Cranes swing, cable spools unroll. A substation's fence rattles as technicians test a transformer the size of a bus. From the road, it looks like any other construction boom. Inside the fence, it is something else. America is building factories for math. Not smokestacks, but racks. Not furnaces, but accelerators. Not conveyor belts, but fiber and cooling loops. The promise behind the noise is simple and immense. If you can stand up enough power, move enough heat, and stitch enough chips into one coherent fabric, you can train systems that write, see, plan, and help millions of people at once. If you cannot, your launch dates slip and your margins thin. In the next minutes, we will turn this build-out into a clear map you can act on. We will translate cranes and cable into economics, show why megawatts and milliseconds now share the same spreadsheet, and explain how sitting, cooling, and contracts decide who ships on time and who explains delays. First, context without jargon. A data center used to be a warehouse for web traffic, spiky demand, many small requests, modest power density. AI changed the recipe. Training runs behave like steel mills for math. Thousands of accelerators must act like one computer for days or weeks. They want steady, high-capacity power, fat network fabrics, and cooling that does not flinch in summer. Inference fleets behave like call centers for tokens. Millions of users show up at lunch and expect answers in under a second. They want proximity to people and to enterprise data, with orchestration that routes easy prompts to small models and wakes bigger models only when needed. Those two modes pull on geography in different ways. Training prefers firm, low volatility power and patient logistics. Inference prefers short fiber paths to the cities where people live and work. Layer on corporate goals for 24/7's low-carbon energy and local rules on water and air, and you can see why America's spend looks like a map, not just a budget. Now the hidden mechanism, the part that turns money into capacity or wastes it. Every AI campus begins with three constraints: electricity, cooling, and interconnection. Electricity is not an on-off switch, it is a queue. You ask a utility to connect a new load measured in tens or hundreds of megawatts. They study the grid, assign you a place in line, and plan upgrades. New high-voltage transformers, switchgear, and lines have their own lead times. The best parcel of land is often the one with an existing substation and room to add a bay, not the cheapest dirt. Cooling is a second physics gate. Power usage effectiveness PUE tells you how many facility watts you need per watt of IT load. Water usage effectiveness WUE tells you how many liters you evaporate per kilowatt hour. In cool, dry climates, outside air and evaporative assists can deliver excellent PUE at the cost of water. In hot or water-stressed regions, closed-loop liquid and refrigerant-based systems protect WUE near zero at the cost of a point or two of PUE. Neither is better in the abstract. Each is a fit to climate, permits, and community expectations. Interconnection is the third gear. For training, you need a fabric that lets gradients fly without starving on the wire. Inside the hall, that means disciplined topologies. Across halls, it means long-haul fiber to partner regions. For inference, it means metro edge proximity to internet exchanges and to the private networks where enterprise data lives. Financing choices amplify or dampen those physics. Long-term power purchase agreements can match your load with steady hydro, nuclear, wind, or solar output and smooth price volatility. Demand response partnerships with utilities let your training scheduler act like a grid participant. Scale up at night when wind is abundant and prices dip. Slow non-urgent runs when a heat wave pushes a city toward the edge. Tax incentives, accelerated depreciation, and local abatements can turn a borderline site into a viable one, but they do not erase queue times for interconnection or long lead times for industrial equipment. The smartest builders treat megawatt math as a first-class product requirement. They do not sign for land without a credible path to power. They do not lock a cooling choice without modeling summer afternoons. Not just winter nights. They instrument everything: temperatures, P95 and P99 latencies, cache hit rates, and utilization, because guesses are expensive at this scale. The build-out bends at a small set of pivotal decisions. The first is sitting strategy. Do you collocate compute with firm, low-carbon generation? Or do you hug users and data? Many are doing both. Remote training campuses near rivers, nuclear corridors, or strong transmission backbones. Metro edge inference halls inside latency triangles drawn around major cities. The second hinge is cooling architecture. Air alone rarely carries dense accelerator heat loads. Rear door heat exchangers and direct-to-chip liquid cooling move from exotic to normal. In some basins, evaporative assists make sense, but require transparent water accounting and seasonal caps. In others, closed-loop designs win permits even if PUE is a hair worse on paper. The third hinge is network fabric. At training scale, InfiniBand offers a proven path. Ethernet evolves fast and wins on ubiquity and cost. Each choice fails if cabling, buffers, and topology discipline slip. The fourth hinge is workload routing. You can spend a fortune to make every hall do everything, or you can design a portfolio. Big models train where power is cheap and steady. Cheap. Fast models answer most questions near users. Hard cases escalate to heavier clusters only when needed. The fifth hinge is community strategy. Some regions welcome the tax base and fund grid upgrades that outlast a single tenant. Others ask hard questions about jobs, water, air permits for backup generation, and heat discharge into rivers. The teams that arrive with heat reuse partners, education pipelines for local talent, and honest reporting on PUE and WUE move faster through hearings and build trust. Consequences flow downhill from those hinges. Power becomes the new rent. The difference between very cheap and merely average kilowatt-hour pricing compounds across hundreds of megawatts and years of operation. Transmission becomes a governor on growth. You can have land, capital, and a plan and still wait because a transformer sits in a factory backlog or a line needs an upgrade. Land markets respond. Parcels with proximity to substations or to fiber exchanges appreciate faster than empty acreage. The supply chain strains. High-voltage equipment backlogs stretch schedules. Skilled trades electricians, controls engineers, welders become their own bottlenecks. Upstream, manufacturers of chillers, pumps, and switchgear run hot. Downstream, cloud services revisit pricing to reflect their own unit economics. Cost per token is no longer a line item only for model teams. It reflects energy price, PUE, WUE, and fabric efficiency. A small improvement in orchestration or caching can pay for itself faster than a headline hardware upgrade if it cuts recurring power and latency penalties at scale. Local economies feel a mix of benefits and trade-offs. Construction booms. Permanent jobs arrive, but not in the numbers of a traditional factory. Public finance shifts. Tax revenue rises. Grid upgrades and water management plans become shared civic projects. Universities and community colleges build programs for data center operations, power systems, and thermal engineering. Environmental policy gets practical rather than abstract debates. Councils discuss discharge temperatures, seasonal water caps, and backup fuel choices. The best operators turn waste into diplomacy, piping warm water to greenhouses, campuses, or district heating. Others get pushback and pauses until plans improve. The winners on the private side close the loop between product and place. They translate latency targets into actual sites. They do not ignore a grid map when planning a product roadmap. They remember that queues and permits are as real as model checkpoints. You can see modern echoes of the build-out everywhere. In cool, river-fed regions, new phases come online in lockstep with substation expansions. In coastal metros, compact inference halls sprout next to big internet exchanges and financial districts where shaving 100 milliseconds keeps users engaged and contracts signed. In arid interiors, water-light designs trade a point of PUE to win permits and protect aquifers. retired industrial sites with strong transmission paper mills, steel plants, coal plants find second lives as compute campuses because the hardest part, the grid connection, already exists. Heat reuse pilots turn into steady programs. As municipalities discover they can warm pools and labs with a byproduct that used to be vented to the sky. Energy strategy matures from offsets to hourly matching. Instead of claiming green on an annual average, operators buy power that aligns with consumption or by hour and use schedulers to chase cleaner, cheaper windows for training. There are real limits and honest critiques. Data centers are not panaceas for local employment. Communities deserve clarity on jobs and on the public works that will outlast any single tenant. Water use is nuanced. Some systems evaporate potable water. Others draw and return non-potable water slightly warmer. Without transparent reporting, trust erodes. Backup generation often diesel raises air quality concerns during testing and outages. Cleaner fuels and battery systems are improving, but they are not universal. Transmission is the slow gear. Raising a campus can be faster than building the line that feeds it. Sitting pits national priorities against local landscapes. And even with abundant power, a missing subcomponent, a transformer, a chiller, a critical switch can hold an entire phase hostage. On the demand side, efficiency breakthroughs arrive fast. Better attention mechanisms, quantization, speculative decoding, and model routing can slash per quest cost and change the shape of needed capacity. Betting only on brute force ignores how quickly software bends curves. From this messy reality, a practical playbook emerges. Start by defining what good means for your product in tokens, latency, and trust, not in abstract performance. If your users reward speed and reliability, design for that. Use retrieval so you do not try to bake every fact into weights. Keep context as short as possible. Quantize where quality holds. Route easy work to small models, and escalate only when needed. Then do the megawatt math early. Before you sign for land, ask 3 questions with numbers. Interconnection capacity today, realistic queue time, and who pays for which grid upgrades. Choose cooling for your basin, not your slide deck. In a water-stressed region, favor closed-loop or refrigerant systems and plan heat reuse with real counterparties, not aspirations. In cooler, wetter climates, consider evaporative assists, but commit to seasonal water caps and public reporting. Treat your schedulers like traders. Training jobs with Slack should chase clean, cheap hours. Inference cannot. Give it premium lanes close to users and to data stores. Expose energy and carbon signals to engineers so they can make informed trade-offs. Build a latency portfolio. Metro Edge for instant responses. Regional hubs for heavier batch processing. Remote campuses for brute force training. Negotiate energy like an adult. Hourly matching is harder than annual offsets, but it aligns with where policy and markets are going and protects you from volatility. Co-invest in grid upgrades that benefit both your campus and your neighbors. It shortens your queue and earns you a durable social license to operate. Above all, invest in observability. If you cannot see utilization, thermal headroom, P95 and P99 latencies, and cost per 1,000 tokens by region and by model, you will guess. At this scale, guessing is expensive. We began with steel, gravel, and a transformer humming behind a fence. The promise was to explain why America I Buildout looks like record spend and how those dollars turn into products you can feel. Now you have the map. Power is rent, queues are real. Cooling is a climate decision. Fiber sets the floor on latency. And contracts with utilities are product design in disguise. The winners in this cycle will not be the loudest press releases or the prettiest renderings. They will be the operators who plan around bottlenecks, place the right workloads in the right places, and treat neighbors and grids as partners. If this episode helped you see where your next megawatt should come from and what it should buy you, stay with us. On Incentive Atlas, we turn complex maps of money and technology into decisions you can act on. Tell me in the comments Which constraint pinches you today: interconnection, cooling, water, or latency, and what we should unpack next so you can ship with confidence.